Hello, I am Stuart MacFarquhar from the University of Southampton, and today I will be presenting my work on the laser crystallization of amorphous silicon and the demonstration of third-order nonlinear optics in the resulting polysilicon waveguides. To begin, I will provide an overview of the previous work in this field and the motivation behind our work, covering the goals of silicon photonics and the technical barriers presented. I will then move on to the fabrication steps, detailing how these processes overcome the aforementioned barriers. Finally, I will present the results of our material characterization experiments, linear loss measurements, and analysis of the nonlinear propagation, specifically two-photon absorption and self-phase modulation. Finally, I will conclude my talk and outline the avenues of future work that these findings could lead to. Silicon photonics is a mature field, with the first demonstration of an integrated silicon waveguide by Soref and Lorenzo in 1985. Since then, the market has grown to an estimated $980 million as of 2019, and is anticipated to reach $4.62 billion by 2027. Significant interest lies in the integration of silicon photonics with electronic systems. However, this currently faces compatibility issues with the standard complementary metal oxide semiconductor manufacture stages. In particular, the 450-degree thermal budget for back-end-of-line integration is too low to allow for the growth of single crystal silicon, and the flip-chip bonding technique does not allow multi-layer photonic structures. Polycrystalline silicon, or polysilicon, is composed of crystalline grains separated by amorphous boundaries, and was first proposed as an alternative material in 1996 by Soref et al. It has since been widely developed as an optical material, and presents numerous advantages over crystalline silicon. Multi-layer systems can be fabricated in deposited polysilicon, and the alternative process, excimer laser annealing of amorphous silicon, is a widely explored topic in microelectronics research. Initial investigations into polysilicon as a waveguiding material were carried out in material manufactured using plasma-enhanced chemical vapor deposition. High-quality photonic components were demonstrated using this method, examples being vertically coupled ring resonators and rapid-response electro-optic modulators. However, PECVD of polysilicon requires high substrate temperatures, rendering it incompatible with the electronics process flow. To avoid this, the laser annealing process from thin-film transistor electronics was adopted, in which a thin film of amorphous silicon is deposited at low temperatures and crystallized by excimer laser exposure. Here, the short exposure times prevent excess heat transfer to the substrate. Using this method, a GHz electro-optic modulator was demonstrated in CMOS-compatible polysilicon. However, linear losses remain high as a consequence of the small grain size, which result in a high amorphous fraction, causing absorption at telecommunications wavelengths. Our work has focused on the minimization of optical losses. To this end, we have carried out continuous wave laser crystallization of amorphous silicon deposited at low temperatures by hot wire chemical vapor deposition. The hot wire CVD process has been selected as it offers low temperature, high purity deposition of low hydrogen amorphous silicon with a low cost and high deposition rate. A buried oxide layer is grown on a crystalline silicon substrate by thermal oxidation to a thickness of 4.7 microns. Then, a 400 nanometer film of amorphous silicon is grown by hot wire CVD with a substrate temperature of 230 degrees. This is the highest substrate temperature in the entire manufacture process, significantly below the back-end CMOS thermal budget. Waveguides then defined by conventional electron beam lithography process and inductively coupled plasma reactive ion etching. This process serves to thermally isolate the waveguides during the following laser crystallization step, promoting enhanced crystal grain growth. Laser crystallization was carried out with a 532 nanometer continuous wave fiber laser with a computer-controlled power output fine-tuned with a half-wave plate and polarizing beam splitter. The laser beam and a white light source for in-situ imaging are focused onto the sample surface using a 10 times objective mounted to a computer-controlled Z-axis stage. The sample is held to the corresponding XY stages by a vacuum clamp. The reflected light is passed through a notch filter to remove the laser wavelength and directed to a CCD camera to provide positioning feedback and in situ process monitoring. The laser was focused onto the waveguides with a 10 micron spot diameter and scanned along the waveguide length at a constant speed. The lowest losses were obtained from waveguides with an initial width of 3 microns and crystallized with an incident laser power of 285 milliwatts and a scanning speed of 0.1 millimeters per second. This example image of the in situ crystallization clearly shows the difference before and after crystallization. This difference in appearance occurs due to the complete melting of the heated volume, one of the advantages offered by the etching of the waveguide structures before crystallization. The thermal confinement that results from this reduces the power requirement, and by ensuring that the waveguide is fully melted, the formation of small crystals, typical to solid-phase crystallization, is avoided. Furthermore, the seeding of crystals from the already crystallized region is encouraged, enhancing the growth of grains along the waveguide length. This reduces the scattering from grain boundaries perpendicular to the propagation direction during waveguiding, limiting a source of optical loss. We investigated material quality using microfocus Raman spectroscopy, comparing the results to a crystalline reference. Before crystallization, the typical amorphous spectrum is seen, whereas after, there is a distinct peak with a Raman shift of 517 per centimetre and a full width at half maximum of 2.72 per centimetre. By comparison to the crystalline values of 520 per centimetre and 2.7 per centimetre, we can tell that the crystallization has induced a material strain and that there is a residual amorphous fraction. The strain, which arises from the mismatch in thermal expansion coefficients between the silicon waveguide and the silica buried oxide layer, reduces the Raman shift of the peak, while the irregular bond lengths in amorphous material broaden the Raman peak. However, the small broadening of only 0.02 per centimetre indicates that the amorphous fraction is low, therefore crystal sizes are large. The optical characterization was carried out using the setup shown here. Laser light was coupled into the waveguides using a high magnification objective, and back-reflected light was directed to a CCD camera to ensure correct focus and positioning. The sample and objectives were mounted on high-precision 3-axis stages, and the waveguide output was isolated to reduce measurement error from scattered light. A second CCD camera was used to easily align the output. Linear loss measurements were carried out with a 1550 nanometer CW diode laser, and the input and output power were measured for a range of waveguide lengths, with the sample facets prepared by cleaving. For nonlinear measurements, the laser source was changed to a 1540 nanometer femtosecond pulsed laser. 2 photon absorption measurements used the same power detector positions as for linear loss measurements, and for self-phase modulation measurements, the waveguide output was directed into an optical spectrum analyzer. Loss measurements taken by cutback were fitted with a linear fit to estimate the transmission and coupling losses from the gradient and intercept respectively. The lowest recorded losses in a 3 micron width waveguide were 2.41 decibels per centimetre, with total coupling loss of approximately 33 decibels. Average losses of 3 decibels per centimetre indicate the repeatability of these results. These losses represent a significant step towards low-temperature polysilicon, offering comparable results to single crystal waveguides, a critical milestone on the road to fully integrated silicon optoelectronics. 2-photon absorption is a third-order nonlinear phenomenon in which the simultaneous absorption of 2 photons excites an electron across the bandgap. The magnitude of this effect is related to the intensity of the electromagnetic field and the material parameter beta TPA, the 2-photon absorption coefficient. As a high beta TPA is detrimental to the performance of a nonlinear device, it is an important variable to characterize. We do this by measuring the output power for a range of inputs with the pulsed laser source and carrying out numerical simulations along the waveguide length. The best fit to the experimental data was obtained using a linear loss of 3 decibels per centimetre and a beta TPA of 7 × 10 to the minus 12 meters per watt, a value which falls within the recorded range for crystalline silicon. Self-phase modulation, the other third-order nonlinear effect of interest to this project, manifests as the broadening of the pulse spectrum with a characteristic dip in the central intensity. Occurring due to the high intensity change to the refractive index, the nonlinear Kerr coefficient, N2, can be estimated by simulating the nonlinear Schrödinger equation and fitting the result to experimentally obtained spectra from a range of input powers. The closest fit to these spectra gave a Kerr coefficient of 3.5 times 10 to the minus 18 meters squared per watt, slightly below the typical crystalline range. The nonlinear figure of merit from our beta TPA and N2 is 0.32, at the lower end of the typical range from comparable waveguides. However, the low nonlinear quality is contrasted by the low optical losses, which provide a low power threshold for the operation of devices in this material. In conclusion, we have demonstrated a low-temperature, low-cost method of fabricating polysilicon waveguides with optical characteristics approaching those of crystalline silicon. By limiting the substrate temperature to below 230 degrees, we ensure that this method is suitable for back-end CMOS integration, and the post-deposition crystallization stage allows optimization of the process for high-density photonics. Record low linear losses of below 3 decibels per centimeter, a 2-photon absorption coefficient of 7 times 10 to the minus 12 meters per watt, and a nonlinear Kerr coefficient of 3.5 times 10 to the minus 18 meters squared per watt indicate that polysilicon produced in this manner may also be suitable for use in nonlinear applications such as the first stages of supercontinuum generation. I hope this summary of my work has interested you, and if you have any comments or further questions, please don't hesitate to send me an email. Thank you very much for your time and attention.